Okay, so let's get started on our solubility of gases lesson. We're going to just take a look at how gases dissolve in water and how their solubility is affected by temperature and pressure. So up until this point, we have focused mainly on solutions that are a solid dissolved in a liquid. So all the work we did with those solubility curves, that was all solids dissolved in water. Okay, so we found by looking at those solubility curves that most solids increase in solubility as temperature increases. So if you just look at this graph down here, you see that both carbon dioxide and oxygen have a downward slope as temperature increases, and this is solubility here. So it's showing that their solubility decreases as temperature increases. Carbon dioxide is much more drastic, oxygen not as much, but it's still got a slight downward slope there. Whereas on your solubility curves graph, most of those were solids, or they were all solids, sorry, dissolved in water, but most of them curved up to the right, meaning that their solubility increased as temperature increases. There were only a few that curved downward. So let's look at why is it that gases have a decreased solubility at higher temperatures? What's different about gases compared to solids when they dissolve in liquids? So first of all, let's just remind ourselves what solubility is, and that is it's how much of the substance can be dissolved in water. So for most solids, like I already said, their solubility increases as temperature increases. So the solution process is considered to be endothermic because it absorbs heat. So what that really means is that most solids require energy to dissolve them. And the reason being is that solids, their particles are packed very closely together, and there's a strong attraction between them. So if we think about an ionic compound, for instance, when an ionic compound dissolves, such as, say, sodium chloride, it breaks apart into sodium ions and chloride ions. So in order to break it into these separate ions, you have to add energy, absorb energy, and often that energy is in the form of heat. So that's an endothermic process. The same thing can be said for a molecular substance, but a molecular substance doesn't separate into ions because it's not made up of ions. It just separates into individual molecules. But that still requires energy because the molecules are attracted to their neighboring molecules. So most processes of dissolving a solid in liquid require energy. Okay, now we're going to see that a gas is quite different, and it's all to do with the nature of the particles in the gas. So the graph above shows the solubility of two gases at different temperatures. The solubility of gases decreases as temperature increases. Therefore, the process of dissolving gases is exothermic, which means heat or energy is released. It's not required, it's released. So it's like a product of the process of dissolving. So why is it? Why do we not need energy to dissolve a gas? Well, gas particles are spread so much further apart than solid particles. Solids are packed closely together. Gases, there's so much space in between each particle that there's literally, or I shouldn't say literally, but basically no attraction between the particles. The attraction that exists is extremely weak. So the attractive forces between gas molecules is weak, so you don't need energy to separate those molecules to dissolve them. So the process actually gives off energy and therefore is exothermic. Okay, so the nature of those particles is very, very different from solids, and therefore the process of dissolving looks a lot different. So this just reiterates what we already said. With most solids, it takes energy to separate molecules and ions so they can be dissolved. So in most cases, dissolving a solid is endothermic, and heat is absorbed or required. Whoops. Okay, so here's some, let's try to relate a dissolved gas in a liquid to something that we're familiar with. So what do you think would happen to a carbonated soft drink? So any sort of pop, Pepsi, Orange Crush, 7-Up, whatever you want to think of. Those are carbonated beverages, and what makes them carbonated, what makes them fizzy, is that they have dissolved carbon dioxide in them. So that's what makes it a carbonated soft drink. Okay, so what do you think would happen to a carbonated soft drink if it was heated and opened? Okay, so there's kind of two things going on here. When a carbonated soft drink has never been opened, when it's closed, the lid is on, or the can has never been cracked open, the contents of the bottle or can are under pressure, and they must be kept under pressure in order to keep the carbon dioxide dissolved in the soft drink, right? So if they're not kept under pressure, what happens is the carbon dioxide will want to escape the liquid and basically escape the solution, and then once it's escaped the solution, it would just dissipate. So as long as it's under pressure, that pressure forces those carbon dioxide molecules, if they do escape, they're forced back into solution, right? They have nowhere to go. So if this is like your can of Pepsi and it's closed, okay, here's the Pepsi inside, some of the carbon dioxide will leave, but there's only this little space at the top. So their gas molecules can bounce around here a little bit, but once you fill this space with gas molecules, you would have to force some of them back in. There's only so much space for those gas particles. So the pressure of having a closed container here forces the carbon dioxide back into solution. I'm sure know from experience that as soon as you do open that, you hear a sound, which is like sort of a whooshing noise almost, like right when you open the can or the bottle, and that is carbon dioxide escaping. So those gas molecules that are above the liquid, as soon as they have an opening, out they go. And once they're gone, you're not going to get them back. So if you let that open can of Pepsi sit for a long time, eventually that Pepsi goes flat because any CO2 that escapes the solution now leaves and enters the surrounding air. So leaving it sit out over time will eventually cause it to go flat, no longer has carbonation. Now heating a carbonated beverage just speeds this process up, because we know that carbon dioxide is less soluble as temperature increases. So less of the gas can be contained in the solution as the temperature increases. So if you heated this up and then opened it, you'd get a very kind of, not violent, but you'd get an explosion of the carbonated beverage out the top, and it would spill everywhere and kind of bubble all over the place, because there would be all that carbon dioxide is just waiting to be released, because it can't, the only thing that's keeping it in this can is the pressure. Otherwise, as soon as it has a place to go, out it will go. Okay, so if you watched the video I posted yesterday, there was a guy who was showing basically this effect, and he used seltzer water, and he had one in a cold water bath or an ice bath, one in a hot water bath, and one at room temperature, and he opened each of them. So you saw like the seltzer water spill and fizz all over the place in the hot one, It does a little bit in the room temperature one, and then it doesn't at all in the cold. And that's because at cold temperatures, you can keep the most carbon dioxide dissolved in the water. Okay, so hopefully you checked that out. If not, you should give that a watch right now. So what I'm going to put here is basically that gas bubbles would be released as CO2 is less soluble at higher temperatures. Okay, so heating a gas liquid solution gives the gas molecules more kinetic energy, right? So as they heat up, they move around more and they have more energy to escape the liquid. So they escape the liquid more easily. So as a gas liquid solution is heated, the solubility of gases decreases and more gas leaves the solution. So let's just connect this to biology, so some sort of real life scenario. So you can talk about drinking carbonated beverages, but there's other applications as well. Organisms that live in water, so fish or any other aquatic organisms, need oxygen gas that's dissolved in the water for respiration. Okay, so on the previous page, on the graph, you saw that the solubility of oxygen decreases as the temperature gets higher. So this means that if water, so lakes, ponds, rivers, oceans, if that water gets warmed or heated, it can cause the release of dissolved oxygen in water, and that can result in death for many aquatic organisms. So heated water from power plants and factories can enter these lakes, rivers, oceans, and cause what we call thermal pollution. So even a temperature change of only a few degrees can have a serious impact on living organisms because there's reduced oxygen dissolved in the water. Okay, so even if we're not talking about thermal pollution, anyone who does some fishing would know that there's certain types of fish, often like really cold lakes or cold parts of the lake are good places to do fishing. And that is because of the higher amount of dissolved oxygen in those colder regions causes more fish to be able to survive in those parts. So some of the lakes in northern Manitoba have excellent fishing and they're just colder lakes. So they make for an excellent habitat for fish. Okay, so I've alluded to pressure already, talking about opening, having a closed bottle or can of pop versus an open bottle. So you can do this at home. It's nothing too fancy. It's just opening a carbonated pop. So either a can or a bottle if you have one at home. If you don't, you've definitely heard the sound before, and that's just like the sound of the gas escaping. It's kind of like a whooshing noise. So opening a bottle of carbonated pop causes a whooshing sound because bubbles of CO2 gas leave the solution. It has the dissolved carbon dioxide and several dissolved solids such as sugar, of course. But the solubility of a gas increases as the pressure above the container increases, right? So as long as you've got pressure there, the contents are under pressure, meaning like there's nowhere for that gas to escape, right? It's a closed container, so that's going to cause an increase in pressure. Then you can keep a larger amount of carbon dioxide dissolved. So pressure, we talked in when we were talking about solids dissolving in liquids, pressure has very little effect on the solubility of solids and liquids. And the reason being is solids and liquids, their particles are already really closely packed together. So pressure really doesn't change much about solids and liquids. There's not much space for them to move closer together, right? They're already pretty tightly packed. So increasing the pressure in solids and liquids doesn't result in a great deal of change. But with gases, pressure has a really large effect on the behavior of gases. So increasing pressure just means you're now forcing those gas particles closer together. And in doing so, you can change a lot of their characteristics. So in a closed pop bottle, the pressure of gas molecules above the liquid causes gas molecules to go back into the liquid until an equilibrium is reached. So what I mean by an equilibrium is, I kind of drew this already last time. Okay, an equilibrium is you're going to have the gas leaving the liquid, and it's got this little bit of space, right? So gas can leave and leave and leave until a certain point at which it can't hold any more gas particles. So at that point, some start to enter back into the solution. And an equilibrium is when for every one gas particle that leaves the solution, another one enters the solution. So it's happening at the same rate. The leaving and entering of the CO2 gas, or whatever gas you happen to be talking about, occurs at the same rate. So gas molecules leave the liquid at the same rate as gas molecules go back into the liquid. Okay, and that's due to the pressure above them. And like they have nowhere to go. There's no escaping. So opening the bottle allows the gas above the liquid to escape, and the pressure is now reduced above the liquid, and this causes more gas molecules to leave the liquid, and that's the whooshing sound that you hear. So the effect of pressure on the solubility of gases is known as Henry's law. So we'll just end with one more biology connection. We'll talk about scuba diving. So a deep sea diver, ones that go to great depths in the ocean, experience really large changes in pressure. So the deeper you go in the ocean, the more the pressure increases. And that's because there's more water above you pushing down on you. So this causes more gas from the scuba tanks to be dissolved in the diver's blood. So the very important thing that scuba divers are trained to do, if like you kind of get trained in stages, when you first learn to scuba dive, you can only go to a certain depth, and then if you want to get more advanced, you get trained to go to deeper and deeper depths, because the deeper you go, the more dangerous it is, and this is one of the reasons. As the diver rises back to the surface, the surrounding pressure decreases. And as it decreases, it makes the gases less soluble in the blood. So those gases actually escape into the bloodstream, and if they escape too fast, they form bubbles in the bloodstream and other bodily fluids, and that can affect nerve impulse transmission, or it can actually block the blood vessels. And it causes something called decompression sickness. Okay, so in order to ensure that this doesn't happen, divers have to ascend, which means rise up in stages at a very, very slow rate. Okay, and another thing they do to combat this is they don't use the same mixture of gases that we breathe in the atmosphere. We breathe in oxygen and nitrogen mixture, but they use helium mixed with oxygen instead of nitrogen. And that's because helium is much less soluble in body fluids than nitrogen. Okay, so there we go. We'll end there for now.